Hello and welcome to another circle theorem video, and we're going to prove some more circle theorems in this video. If you haven't already done so, I encourage you to watch part 1 where I prove 3 of the circle theorems. So we're just going to continue that journey in this video and look at a few more. So as always, pause the video before I go through these proofs to see if you can do them first. Now the key to most of these proofs is to draw in radii. So if you're ever stuck, just draw in some radii and hopefully something will jump out at you. So let me get my line tool out and I'm going to draw a radius from the center of my circle to one of the vertices. And then I'm just going to repeat that process to each of my vertices in my quadrilateral. So I'm going to draw 4 of these in total. So that's number 3. And then the last one, we're going to go from our center up here. Okay, now let's label some angles. So what do we know about these triangles that have been created? Well, hopefully you can see that here we've got a radius and here we've got a radius. They must be the same length, therefore this is an isosceles triangle. And what do we know about isosceles triangles? Well, base angles are equal. So this angle here is equal to this angle here. We don't know what they are, but we know that they're the same. So we can just label those. If we label them A, now we can repeat the process all around the circle. So now if we focus on these 2 radii, we've got another isosceles triangle. Therefore, these 2 angles that I'm drawing in blue must also be the same. We can clearly see that they're different to A. So let's label those B. So these, let's label B. Let's keep going. So these 2 side lengths are the same. Therefore, these 2 angles in magenta are the same. Let's call them C, just to be consistent with the alphabet. And finally, we can see that these 2 side lengths are the same. So these 2 angles in green are the same. Let's call those D. Okay, what else do we know about angles in a quadrilateral? Well, angles in a quadrilateral sum to 360 degrees. That's something you learn very early on in your school. But yeah, all of these angles add to 360. So this angle here, plus this angle, plus this angle here, plus this angle, they sum to 360 degrees. So if we can write an expression for these angles. So this angle here is A plus B. So A plus B plus B plus C, B plus C, plus C plus D, C plus D, plus D plus A, D plus A. So when we sum those together, we get 360 degrees. We can do a bit of simplification. We've got A plus A, that will give us 2A. B plus B, 2B. C plus C, well that is 2C. And then D plus D is 2D. So that gives us 360. We can simplify this even further. Notice everything is divisible by 2. So if we divide everything by 2, we're just left with A plus B plus C plus D equals 360 divided by 2 is 180 degrees. Now, there might be something that jumps out at you. If we focus on this angle, what we're saying is that this angle plus this angle is 180. Well, if we have a look at the labels that we've given, this angle is A plus B, and this angle is D plus C, or C plus D. So we can see that this angle plus this angle must equal 180 degrees. Now we've proved it for these 2 angles, but what about the other opposite angles? So this angle here and this angle here. Well, let's just write down what these angles are. So this is A plus D, A plus D. And then this angle here is B plus C, B plus C. But notice that this expression that I've just written out is exactly the same as this expression. Addition is commutative. The order does not matter. So this must also equal 180 degrees. And let's just box our angles. So this one was A plus D. And this angle here is B plus C. But notice these 2 expressions are exactly the same. The order that we add things doesn't matter. You know, 3 plus 2 is the same as 2 plus 3. So we've just proved that opposite angles in a cyclic quadrilateral always add up to 180 degrees. Okay, moving on to the second circle theorem. It says the 2 tangents to a circle from a point are equal. So notice up here we've got 2 tangents, the lines in green. They start at this point here, and they go to this point on the circle and this point on the circle. So these two side lengths, they are equal. So that's what we're going to prove. We're going to have to prove it over here. And again, whenever we're dealing with proofs, the first thing to do is to draw in some radii. So let's do that. So from the center, let's go to A. And let's do exactly the same to B. So we can clearly see that these two side lengths are the same because they are both radii. Now I'm going to draw in one more line from the center, but this time I'm going to go all the way up to C. And notice I've got two triangles. So with these two triangles, there are two angles in these triangles that I already know. And that is this one over here and this one over here. Now I can say with some degree of certainty that this angle is 90 degrees and this angle is also 90 degrees. Now, how do I know that? The reason I know that is because we've got a tangent that meets a radius. And whenever a tangent meets a radius, they always meet at 90 degrees. So these two lines, tangents and radii, that meet together are always perpendicular. And I'm not going to prove that in this video, and you don't need to prove it in your exams. You can just take that as a given that a tangent always meets a radius at 90 degrees. So we've got two angles that are the same. We've got two side lengths that are the same. So you might be smelling some congruence coming up, and indeed you would be correct. So in order to prove that two triangles are congruent, we need three pieces of information. At the moment, we've only got two pieces of information. So what else do we know is the same between these two triangles? Well, that would be this side length over here, because it is shared. So this side length is shared between two triangles, so it must be the same. So now we've got our three pieces of information. Can we prove that these two triangles are congruent? Well, we've got right angles that are the same. We've got a hypotenuse that's the same and another side length that is the same. So yes, we can prove that they are congruent, and that would be through the RHS axiom. So if you're a bit wobbly with congruency and similarity, I do have a video series dedicated to this topic, so please feel free to go back to that playlist and watch that. But RHS, that stands for right angle, hypotenuse, side. So because we've got two right angles that are the same, we've got a hypotenuse that's shared, and we've got two side lengths that are the same, we know that these two triangles are congruent. And with that, we can say for sure that the corresponding side lengths and corresponding angles are also congruent. Therefore, we can say that this side length here, so side length AC, must be congruent to this side length CB. So I've just put a concluding statement at the bottom here that says that AC and CB are the same length because of RHS congruency. Okay, this is the last circle theorem that we're going to look at in this video, and it is called the alternate segment theorem. So it states that the angle between a tangent and a chord is equal to the angle in the alternate segment. Now there's a lot going on there. It sounds quite complicated, so let me just run through it quite slowly. So the angle between a tangent and a chord. So if this is our tangent and this is our chord, well, the angle between these two lines is this angle here. So I'm just going to highlight that in red. So that is the angle we're focusing on. Now we're saying that that angle is equal to the angle in the alternate segment. Now I don't like the phrase alternate segment, so let me just show you what angle we're talking about. So remember, this is the chord that we're connected to. So remember the tangent and the chord. All we need to do is look at opposite that chord. So opposite that chord is this angle here. So that is the angle we're referring to. So these two angles are the same. Okay, so let me just show you with the other angle. So let's say, so we've still got this tangent, but let's say we are connecting to this chord. So the angle between this tangent and this chord is this green angle. Okay, so what we do is look at the chord that it's connected to, and opposite that chord is this angle. So these two angles are the same. So although they give sort of a formal definition of alternate segment, I think this is a much easier way to remember which angles are paired up. Okay, so let's look at the proof. So, as always, I'm going to draw in my radii. So, There's one of them. And then there's my other one. So I'm just going to connect one from the center to each vertex. There we go. And now let's do a bit of labeling. So let's use blue. So let's call this angle angle A. And again, we've got an isosceles triangle, so this angle is also A. And let's use, I don't know what colour, let's use orange. I don't think I've used orange very often today. So let's say, well, first of all, we can see that these two side lengths are the same. So we've got another isosceles triangle. So let's call that B, and therefore that one is also B. Okay, now let's look at this angle here. So how can we write an expression for this angle? So let me just draw a line to show which angle we're referring to. Well, this is going to be 180 minus A minus A, so 180 minus 2A. And if we do the same with the orange angle, so this angle here, this is going to be 180 minus 2B. So hopefully you're following along at the moment. Now let's work out this angle. Now there's a couple of ways you can work out this angle. Just pause the video and see if you can use one of the circle theorems that we've talked about previously to work out to write an expression for this angle. Well, hopefully you remember from part 1 that the angle at the center is twice the angle at the circumference. So if this angle is A plus B, well, this angle must be 2A plus 2B. Okay, and you can also prove that if you want to. We know that these angles add up to 360 degrees. So if we take this blue angle and this orange angle away from 360, you should be left with 2A plus 2B. Okay, but this is obviously a much quicker way of working it out. So now we've done that, let's write an expression for this angle. So again, we can see that we have a isosceles triangle here. So these two angles, these two maroon angles are the same. So how do we calculate them? Well, first of all, we need to take this angle away from 180, and then we need to half it. Okay, because we know that these three angles add up to 180, but these two are the same. So if we take this angle away from 180, that will be then we'll be left with sort of the sum of these maroon angles. But because we know they're the same, we can just half our answer. So it's going to be 180 minus this angle, so minus 2A minus 2B. And then we just need to divide that by 2. So that is this angle here. And I can simplify that. So I can divide everything by 2. So this is going to be 90 minus A minus B. And now we've written an expression for the maroon angle. Let's just pause and think about what two angles we're trying to prove are the same. So the angle between the tangent and a chord. So this angle here, let's say this angle. That needs to be the same as the angle in the alternate segment, which is this angle here. Okay, so this angle over here on the right hand side, well, that's just going to be the maroon angle plus the orange angle. So what's that going to be? Well, it's going to be 90 minus A minus B. 90 minus A minus B, and then we're going to add on the orange angle, which is just B. So it's going to be plus B, which we can clearly simplify. Well, the B's will cancel out. That's all we're going to be left with is 90 minus A. So let me box that. So that is this angle over here. Now, this other angle that I've drawn in black, what is that? Well, we've got a tangent that meets a radius. And we know that when a tangent meets a radius, it forms an angle of 90 degrees. So this angle is 90 degrees. So the angle in black, we just need to take away the angle in blue. So it's going to be 90 minus A. And lo and behold, they are the same. So we have just proven that we've proven this statement basically. And again, it would work if for this angle over here. So let me just highlight or draw in this angle. So this angle, if we were to go through the same business, that would be the same as this angle over here. And that is known as the alternate segment theorem. Now, this is the last proof that I'm going to go through for circle theorems, and I do appreciate that there are many different types of proof that you can do to prove these circle theorems. So, for example, this last one that I went through, it looks quite complicated. There is probably a much easier way to prove that these two angles are the same, but this way that I went through with you just made sense to me. So, in the next few videos on circle theorems, we're going to put this into practice. And we're going to try and calculate some missing angles using these circle theorems that we've learnt about over the last 2 lessons. So hopefully you'll join me for that, and thanks again for watching. Take care.